The Backdated, Episode 8, The Sun's Missing Silver. For years, astronomers pointed their instruments at the sun and kept finding the same problem. There wasn't enough silver, not a small shortfall. A gap big enough that it didn't make sense given everything else we know about how our solar system formed. Scientists couldn't explain where it went. Last month, a team running one of the most complex simulations ever attempted on a single atom finally found it. This is the Backdated. This is the story of the sun's missing silver. Before you can understand why this counts as a real scientific mystery, you have to understand something a little counterintuitive. Astronomers don't study the sun by mining it. They study it by reading light. The sun is almost entirely hydrogen and helium, roughly 98.5% of its total mass. Everything else, all the heavier elements like iron, copper, and silver, makes up just a sliver of what's left. But those trace elements matter enormously to scientists because they act like a fingerprint of cosmic history. Silver, specifically, is thought to form only in one of the most violent events in the universe, a supernova, the death explosion of a massive star. When astronomers can measure how much silver exists in the sun and in other stars, they can start reconstructing where that silver came from and how heavy elements have spread across the galaxy over billions of years. The way scientists actually measure this from 93 million miles away is through something called spectroscopy. As light travels out from the sun's core, it passes through the sun's outer layers, and atoms in those layers absorb light at very specific wavelengths. If you break sunlight apart into a spectrum, like a rainbow spread out and examined closely, you'll see dark lines where certain wavelengths have been absorbed. Every element absorbs a slightly different pattern, its own unique fingerprint. By studying those fingerprints, astronomers can calculate what elements are present in the sun's outer layers and roughly how much of each one is there. And that's exactly where the problem showed up. When scientists read the sun's silver fingerprint, they consistently got a number that was too low. Too low compared to what exactly? This is where the mystery gets its teeth. Scientists have another way to check the sun's original chemical makeup: meteorites. Specifically, an extremely rare and ancient type called Sema chondrites. Meteorites that formed from the same raw, primordial material that created the entire solar system, including the sun, 4.6 billion years ago. Because Sema chondrites are essentially frozen leftovers from the sun's own birth, scientists expect their chemical composition, including silver content, to roughly match what's inside the sun today. But when researchers compared the numbers, the sun's spectral silver reading came in noticeably below what the meteorites suggested it should have. Either the meteorite record was wrong, or the standard way of reading the sun's spectrum was somehow missing silver that was actually there. For years, that gap sat unresolved, a persistent inconsistency in one of the most well-studied objects in the entire universe. And that inconsistency mattered more than it might sound. The sun is, in a very real sense, the calibration point for everything astronomers think they know about how stars form and evolve. If scientists can't accurately measure something as fundamental as silver content in the one star they can observe up close, in extraordinary detail, every day, it raises uncomfortable questions about how reliable those same measurement techniques are when applied to stars trillions of miles away, stars astronomers will never be able to double-check against a physical meteorite sample. The team that finally cracked it was led by Sema Caliskan, a researcher now working as a postdoc at the University of Liège in Belgium. Their idea was straightforward to describe and brutally difficult to actually pull off. What if the standard method for reading a silver atom's spectral fingerprint was too simple and was systematically underestimating how much silver was really there? Here's the technical wrinkle at the center of this whole mystery. When light hits an atom, that atom doesn't just passively absorb it in a clean, predictable way. Complicated physical effects, what researchers call non-equilibrium effects, can alter exactly how an atom interacts with light passing through it, effects that vary significantly depending on which specific element you're looking at. Older models used to calculate the sun's silver content had never fully accounted for these effects for silver specifically, mostly because properly simulating them is extraordinarily difficult. Every element behaves a little differently, and modeling those quirks accurately requires enormous computing power. As it turns out, no research team had ever successfully built a full non-equilibrium simulation of a silver atom before. Caliskan's team decided to be the first. Other scientists had actually tried to solve this exact problem before, with limited success. Their simulations, by comparison, were relatively simple, treating atoms in a more idealized, textbook way that didn't capture how messy and atom-specific these non-equilibrium effects really are. It's the kind of scientific gap that's easy to describe in a single sentence and brutally expensive to actually close. Everyone suspected the old models were probably oversimplified, but nobody had the computational resources or the patience to build something more accurate for an element as specifically tricky as silver. To do it, they turned to the tetralith supercomputer in Linköping, Sweden, one of the more powerful scientific computing clusters in Europe, and built out detailed physical simulations of exactly how a silver atom absorbs and emits light once you account for all of those messy, non-equilibrium quirks that earlier models had simplified away or ignored entirely. The results lined up. Once the team ran their more sophisticated model, they found that accounting for these previously ignored effects changed the picture significantly. The sun, according to their calculations, actually holds roughly 55% more silver than earlier measurements had suggested. That's not a small correction. That's the missing silver, hiding in plain sight the entire time, not because it wasn't there, but because the older method used to read the sun's spectral fingerprint was systematically undercounting it. It's not a perfect exact match to the meteorite numbers. There's still a modest gap between the new solar measurement and what CI chondrites suggest. But it closes the gap enough that researchers say they can rule out any exotic or extraordinary explanation. No lost population of silver hiding somewhere unexpected in the sun's interior. No strange cosmic process nobody had accounted for. Just an atom that was more complicated to read accurately than anyone had previously modeled. There's something worth appreciating in how unglamorous the actual breakthrough was. Nobody found a hidden reservoir of silver. Nobody discovered some dramatic new physical phenomenon happening inside the sun. The mystery was solved by getting more honest about how difficult it actually is to simulate a single atom precisely, and then putting in the computational effort nobody had been willing or able to put in before. Nearly 5 billion years of the sun quietly holding on to its silver the whole time, and the only thing standing between scientists and the answer was a more accurate simulation. Caliskan and her colleagues aren't stopping with the sun. Their next step is applying the same non-equilibrium modeling approach to other types of stars entirely, checking whether similar hidden gaps have been distorting silver readings across the galaxy, not just in our own solar system's home star. If the same undercounting problem shows up elsewhere, it could mean astronomers need to revisit silver measurements across a huge range of stellar research, essentially recalibrating a small but important piece of how we read the chemical history of the universe. The research was published in the journal Astronomy and Astrophysics this past July. It's a strange kind of mystery to sit with. Nothing was ever actually lost. The silver was there in the sun the entire time, sitting quietly in plain sight for billions of years, waiting for a simulation precise enough to actually see it. Sometimes the missing piece of a scientific puzzle isn't hiding somewhere exotic at all. It's hiding in the assumptions built into the tools used to look for it in the first place. There's a version of this story that could have stayed unresolved indefinitely, another quiet inconsistency that astronomers simply learned to live with, footnoted in papers for another decade or two until computing power eventually caught up. Instead, one team decided the gap was worth chasing down properly, spent the time building a simulation nobody had managed before, and found that the sun had been holding on to its silver in full view the whole time, just outside the resolution of every tool anyone had previously pointed at it. If you want us to dig into another case like this one, let us know in the comments. This has been The Backdated.